that charge away from the iodine enough to expose a little positive region, and that's called a sigma hole. And the reason that's interesting with molecular crystals is because you then have a single atom which is partially electropositive and around the outside partially electronegative. So we don't have the iodines interacting like this because that's positive and that's positive. What ends up happening is we have this kind of interaction, and that's called a halogen bond. And we have those here. These halogen bonds that go all the way through the crystal and make these nice iodine channels, which we think might be interesting for conductivity. Lots of delocalized charge moving around. But also in this crystal, what we have are the stacking interactions, the pi stacking dispersion forces that are holding the crystal together and stabilizing it in a third dimension. So this is the sort of thing we're dealing with on a daily basis. Polymorphism is really where my specialism is, and that is effectively the ability of a molecule to pack in a number of different ways, not just the most efficient, so it's the densest. Any molecular crystal can pack in a number of ways if exposed to the right parameters, the right variables. So, for example, if we environment A, let's say we use physical vapor transport, we get this packing, and if we recrystallize it from ethanol, environment B, we get that kind of packing. Now, what you need to pay attention to with these two polymorphs is in form 1, we've got the red end pushed up against the green end, so we've got that kind of interaction. In form 2, what we have is each end is pushed against the middle of the molecule, so that interaction is going to differ. So, by changing how these molecules interact, we change the bulk properties of the material. A good example of this is paracetamol, the painkiller. Paracetamol has a number of different known forms. If you dissolve it in ethanol and recrystallize it, which is the standard means in which to crystallize ethanol, this is the type that's found in pills that you would take, you would buy in the pharmacy. Gives us the thermodynamically most stable monoclinic form of paracetamol. This is produced on an industrial scale because it's nice and easy to make. However, if you crystallize it from the melt, that is, you just take the molecules as a solid, you melt them and you slowly cool it, you get form 2. Now the interesting thing about form 2 is it's metastable, which means at the temperature in which you're measuring, it's not the thermodynamically most stable. Given the chance, given an activation energy barrier, it will transform to the thermodynamically most stable form. However, it does seem to be fairly stable at room temperature, and the reason this is interesting is it's got a higher dissolution rate, which means when it gets to your stomach and hits aqueous acids and water, it dissolves faster and gets into your bloodstream faster, so it's more efficacious. It works better as a painkiller. And it's also more compressible, which means if you're making this on a ton scale, tons and tons at the same time, it's easy to process and press into pellets. However, the trade-off is, do you invest lots of money into heating up lots of paracetamol to melt it, or do you just recrystallize it from ethanol and accept the fact that it's going to be slightly less efficacious? In this case, the heating is too expensive, so form 1 is always the one seen in tablets. The only time you're going to see it in tablets is if someone comes up with a room temperature, room pressure way to make form 2 without lots of hassle or toxic chemicals or additives. A very famous case of this is that of ritonavir. Anyone that works in polymorphism or organic pharmaceutical crystal growth would have heard of ritonavir. It's a protease inhibitor that basically stopped people dying from AIDS. So if you look at the dotted black line in this graph, which is the important one, that's the number of deaths from AIDS, the disease. And when ritonavir was released, you see this drastic decline. It went from 50,000 deaths per year to 18,000 deaths per year. So people can then live with AIDS without it being a death sentence. So it was a big thing. Abbott Laboratories made billions off ritonavir. They sold it all over the world. It was a blockbuster. It was changing the world. Then, all of a sudden, it stopped working. People were taking it, and ritonavir just wasn't doing its job anymore. And they initially didn't know why. People were taking it, and it just wasn't doing what they needed it to do. What had actually happened was there was a second form of ritonavir, second polymorph, here, form 2, that they hadn't found. So all of these pills that they distributed around the world were form 1. People were taking it, it was dissolving, and the dissolution, it was going into the blood and doing its job. The molecule was fine. However, form 2 appeared, and all of a sudden, it wouldn't dissolve. Because the dissolution, how fast it dissolves, is exclusively a function of the molecular interactions between these molecules. So basically, it had gone to a more thermodynamically stable form that wouldn't dissolve, completely insoluble. So people were taking it, and it was just going straight through the body and being excreted by the kidneys. Through the gastrointestines. Now the problem with this was, now that form 2 had appeared, they couldn't make form 1 again. Literally could not make it again. The factories, they were producing it, they were getting form 2 every time. They even built brand new factories to try and stop this form 2 from appearing. It worked for a couple of weeks, and then form 2 appeared. So globally, all at once, a tiny speck of form 2 appeared, and it converted the entire supply around the world. Phenomenal. And Abbott Chemicals lost lots of money because other people started developing protease inhibitors that were very similar. Did the same kind of thing. So basically, any property of the bulk material can be changed through polymorphism. Morphology, hardness, color, melting point, conductivity, band gap. Down in the bottom right, there is a picture of chocolate, and you probably see this fairly often in Japan because it gets so warm. If you've ever come across chocolate that looks like this, and you don't quite know what's going on, the cocoa butter in chocolate has a very specific polymorph. The one that they make, the one that you taste, it has particular taste, particular texture. If you warm chocolate too much, it changes polymorph, and then it stays that other polymorph, which looks like this. So all this means is the chocolate has gone over a certain temperature, and it won't revert back to the old polymorph. Chocolate companies spend millions and millions developing techniques in which to get their polymorph absolutely spot on for how the chocolate tastes and melts and whatnot in the mouth. Rubrene, a molecular crystal, as far as I'm aware, still has the highest conductivity of any molecular semiconductor. It's used in OLEDs and OFETs, but there are a number of different polymorphs. The orthorhombic, luckily, yes, sorry about that. Still good. Yes. It looks fine at the moment. Let's put this over here. Okay. The orthorhombic form is the most conductive. So luckily, if you're growing rubrene to build devices on semiconductors and whatnot, chances are you'll end up with the orthorhombic form, which is the most thermodynamically stable. But it's worth knowing, if you are going to build a transistor or an OLED on an organic crystal, just because you have the right molecule doesn't mean you're going to have the right crystal when you come to building your device on it. Okay, and that's worth remembering with regards to the conductivity of the material you're going to work on. So organic crystal growth is basically a function of making a supersaturated system, be that in solution, be it in physical vapor transport. Typically, a crystallization experiment is you dissolve your solute in a solvent, you then increase the supersaturation. It can be done in a number of ways. You can have an evaporatively driven crystallization where you let the solvent come off bit by bit, and that increases the supersaturation here. So you dissolve more and more and more as temperature increases, and then you filter out any nucleation sites, and then you cool it down, and it won't crystallize straight away. You need that that area of supersaturation. And then when it starts to crystallize here, it will just crystallize and take all the solute out of the solution. You can also do it by cooling, removing the solubility by using an anti-solvent. So you can add an anti-solvent to the system, and that makes the solute less soluble. Physical vapor transport is another one, fairly recent way of crystallizing materials, but then you use a saturated gas to carry the molecule into different temperature zones. Just a quick point on classical nucleation theory, where crystals come from, why they grow. This is just a very basic graph. It's actually based on the formation of water droplets, so there are a lot of assumptions in classical nucleation theory, and for most systems it seems like this is not actually